So it's my privilege to introduce Professor Tobin Marks. Professor Marks and me went back almost 30 years, I think, right? Okay, so I know him extremely well. So Tobin is a national treasure of the United States. Okay, so that's the statement I would like to give to him. Okay, and he received his PhD from MIT. Okay, and from his boss, also very famous, Professor Cotton. Okay, right, was his PhD supervisor. So after that, then I don't need to go through the laundry list of his affiliation, all the different kind of things right now. But then I just try to say few things. Okay, then you will agree with me, right? Why he is a national treasure of the United States. Okay, first he won the most prestigious award from the United States, a science medal, National Science Medal, and received that from the President of the United States. Okay, and then he's I think the recipient. Okay, actually Academy member from how many I cannot count it. Right? Okay, U.S., Israel, Germany, Chinese, and so on and so on. Right? So he received 250 awards. Okay, so if I want to list all of those awards, right, then I will stand here by the end of this session already. It still cannot count all his awards, right? So he actually, is one of the role model for me and for a lot of young scientists also, right? And with his broad interest, he is encompassed in so many different fields, and each field he become one of the really frontier researcher, right? So when he talk about those flexible electronics and also electroactive material, that's just one area. Everybody may think that's one of his major area, but one of his major area is catalysis. Okay, heterogeneous catalysis, and to really make a dramatic impact to the society. Okay, so he published more than 1,500 papers, and also received about 250 patents. Right? Okay, and so this is tremendous, right? But the most important thing is the societal impact. Okay, through all his broad interest in the many different areas, and produce very viable technologies. So spin off 15 companies, right? And the 15 company, do you know what's the value of those companies? $100 billion US dollars. Okay, for the value of those companies, right? So can you imagine? 100 billion, 1,000 亿美金啊，就是about 8,000 million of the Hong Kong dollars. Okay, so this is an impact of a single scientist created to not only the scientific field, but also really takes all the wonderful science and then really converts that into technology translation and really create societal impact. With that introduction, okay, please join me to welcome Professor Tobin Marks.
Alex, wonderful introduction. I hope I can do as well. So it's a great pleasure to be here today. This is not my first visit. I always enjoy visiting Hong Kong and visiting the universities, meeting the young people. And I thought today I would talk about an area of science that we've been involved in that starts with some dreams. And we're going to be talking about flexible electronics. And it was really a dream 10 years ago, but now we begin to see it as a reality. And the other part of the issue is, so if I had a flexible transistor, what could I do with it? How could I serve humanity? And so was working just a couple minutes ago. So here's a grand challenge for chemists, for physicists, for material scientists, for biologists, to make ductile electronic circuitry that you could stretch and bend, but would have very high performance. And what would you do with it? RFID tags, so that when you go to the supermarket, the transmitter can look at your whole shopping basket and find the price of each item, and then you just leave the store after you pay, of course. Display backplanes, we're going to talk a lot about those. E-books, bioelectronics, smart packaging, smart displays, photovoltaics for solar cells, the Internet of Things. And imagine that we don't have a multi-billion-dollar fab line to process the chips, the transistors we want to make, but rather we'll print them the way we print a newspaper. And the power there is every day they print a new New York Times or a London Times, whatever. So you can reconfigure electronic devices at amazing speeds. And this is one example here. Here's a printed backplane, and here's, in fact, a printed solar cell. We won't get down to the 8 nanometer node, but there's a huge number of things we can do at this scale. But it's not, so then you say, oh, it's easy, just get yourself some inks and print them. It ain't that easy. So there's a lot of science we need, unconventional materials. We're going to need N and P type semiconductors if we want CMOS. So if you say, how do I make an N type organic conductor and make it semiconductor and make it air stable? That's not a simple task. High K gate dielectrics, tunable optical properties. Maybe I'd like a whole array of transistors that are completely transparent, or ones that have some other optical property. And this idea also, some of the parts of this technology will be hard matter, whether it's metal electrodes, whether it's, you'll see examples of oxide materials, and how do we marry them, synergize them with soft matter, like transistors made of flexible polymers. And a lot of people are excited about this area, and these are just some review articles. And let me start. I don't know, this is for the students. How does a transistor actually, what does a transistor do and how does it work? So it's going to have 3 electrodes, source, drain, and gate. It's going to have a semiconductor, and it's going to have a dielectric. And it's a switch. It's a switch to turn the current that's going from here to here on and off. And you say, well, I can do that with a light on the wall. But the idea is to do it at very high speeds, but also if I can do this very simple switch, and I combine many of them, I can make amplifiers, I can make all sorts of electronic devices. And so if I have a bias between the source and drain, but no bias between the source and gate, nothing happens. But on the other hand, if I do this, oops, sorry, let me go back one. If I put a bias here, then what happens is called the field effect. But what will happen is we'll generate carriers in the semiconductor, and this is called the channel. And of course, the motion of the carriers is the electrical current. How the mobility times the density of those carriers will tell us the current. And they'll be stabilized in the channel by the dielectric. And the data that we'll see, just to get you ready, this is an output plot. So what you see, this is the voltage between the source and the gate, and this is the current. And as I increase that field, I get more and more carriers until it saturates. I can also, this is called an output plot. I can plot it as a transfer plot, and in this case, I've got the VG, the gate voltage by the current, and you'll see that this sharpness here is a very important part of the transistor. We want it to turn on abruptly, on and off abruptly, and if I plot it a different way, I can get the mobility. So what do I want to do to optimize the performance of the transistor? The mobility, we'll talk a lot about that. The on and off ratio, the threshold voltage. If I have to have a 20-volt battery to turn the transistor on or off, that's bad. The subthreshold swing is the steepness here, and the dielectric capacitance. And this is a very interesting topic, and it's one that Intel spent a huge amount of money on to go from silicon dioxide to hafnium dioxide. We'll say a little bit about that. So we like to optimize them, but we want to do it as chemists. I haven't even shown you what is in here, but it's not like a hard piece of silicon. It's going to be things that we create, that we tune in all sorts of fascinating ways. Just to orient you, so a liquid crystal display, like this iPhone here, uses as the semiconductor amorphous silicon. And you can all hiss and boo because this is really a very lousy semiconductor. The mobility is about 0.5. The on-off ratio is respectable. This is not a high mobility. I'll show you much higher. And it only works to give N-type semiconduction. And I want both N and P if I want to make a really good circuit. But this is where the state-of-the-art was maybe 10 years ago. So let's go on from there. Let me talk about the lecture then. So throw out a lot of things you thought about silicon electronics. We're gonna do some very, very different things. So we're going to start with polymer semiconductors for ductility. Ductility means I can bend, I can stretch, I can twist, and you can see here this is actually our part of our campus in the background, and the student has this circuitry on a piece of plastic. We're going to talk about how do you make an organic material stretchable and still have good carrier mobility. Everything that everyone has normally done made dense films. You know, people say, well, why do you want a film with a bunch of holes in it? And so we're going to talk about new opportunities for porous semiconductors. And then we're going to talk about ones where we actually have electrochemistry involved. And then we're going to flip things and talk about transparent conducting oxides. I think everybody here has heard of ITO, right? But the field is much broader and much more interesting than that. And so here's an example of some transistors on glass, completely transparent, a whole bank of transistors, oxide transistors, and we're going to change their properties. And then I want to take this area and that one, and I want to hybridize them. And you say, what? Mixing inorganic and organic? That's like two different departments at a university. Maybe even worse than that. And so we're going to talk about hybrid materials, and we're going to I'll just show you, we have a machine that stretches them. And to do that and still have really good mobility is fascinating. So let's now sort of zero in more on, we talked about this kind of field effect transistor, okay? But now let's say we're going to do something different. The dielectric here is going to be a solution. And so this is called an electrolyte gated transistor. And again, these are the carriers, plus and minus. And then let's turn on redox. See, this is the semiconductor. Now, look what I've done. I've created carriers not only by the field effect, but by redox chemistry of the semiconductor. And then you can do things that you never imagined doing. And we'll talk about that. So the carriers are electron holes. The channel where the carriers move is this very thin layer at the interface. And this is a whole different ballgame. And in fact, people have called it Iontronics. So we're going to mix hole and electron conduction in the semiconductor with not only by the field effect, but by doing chemistry. Then you might say, yeah, but how fast can you do that? Can you make it reversible? So we'll see. So let me start with a collaboration with a Japanese group. And this is the Sumeya group, and Binghao Wang, who was a graduate student with me, said, I'd like to postdoc in Japan, because this group really knows how to make flexible materials. And what you're going to see is an interplay, for our part, of things you can do. So this is an N-type semiconductor. This is a P-type, and I'm going to mix it, either this and that, with this photoresist, which when I cross-link, photo-cross-link, i.e. pattern, and this is an example of some of the patterning you can do, there's a phase separation. So what happens then is we have the polymer blend, and when we do the photochemistry to make this cross-link, you get a phase separation. So when you're all through, you've been able to create patterns with the semiconductor on top of the photoresist. This is the work of Binghao Wang, and what you can see is we do all kinds of time-of-flight sims, GWACs. Have we really gotten phase separation? How much have we gotten? And then what is the mobility? When we phase separated, how pure is the semiconductor? Does it have good mobility? And so you can see, yes, it has good mobility. And Antonio Facchetti is a collaborator. He's been a collaborator for many years, incredibly talented chemist. And so we made devices. So this is called an inverter here. And the beauty of the Sumeya group is, so this particular polymer is called perylene. And you can see this is a needle. And you can take the whole circuit and just bend it as if it were a piece of cellophane. And ultra-flexible devices, patterning, you can see very simple patterning, and these are air stable. So let me turn to some work of Dan Zhao. And many films that we would make for semiconduction, let's say a molecule, so this is one that was made by vapor deposition. If you try to bend them, they crack. And if you ask, well, why does it crack? It cracks because they're grain boundaries. And suppose we could do chemistry. So this is the semiconductor, and so this is a crystalline film. So the cracks, suppose we could fill the cracks with this material, where if you think of like likes like, so this would want to associate with the grain boundary as with this, and here in the middle is a flexible semiconductor, and this is the work that Dan did. And so we basically plasticized the grain boundary. So we can make a transistor that you can bend back and forth. And this polymer binder is just called PB1. So 5 weight percent, and you can see that the mobility drops a little bit as you bend it, but not as much as if you don't have the polymer binder. So you might say, yeah, but how the heck do you know that that's really what you've done? So we do a lot of microscopy, where we see as we add more and more of the polymer binder to plasticize the grain boundaries, you don't see cracking anymore. But also we can do EDS, scanning electron microscopy, and you can see this guy has sulfur, these have fluorine. So with the EDS you can do a spatial mapping of the elements present. And you can see that it's behaving just like we predicted. And this is grazing incidence, wide-angle X-ray diffraction. And it says basically the host polymer is still, or the host organic material is still crystalline. So now let me ask a question. If you look at typical transistor engineering, you don't want holes in the semiconductor. You don't want porosity. But what if you could do that? And we're going to do it with organics. And if I could make a porous semiconductor, you might say, yeah, but what's it good for? Well, it could be a sensor. So if I make it porous, I have much more, this is called a ChemFET. I have much more surface area, and you can see the one with porous has a much higher response to NO2. But this is even more interesting. So this is an electrochemical transistor. It looks like a transistor. Here's the polymer. But there's a liquid electrolyte here. And the liquid electrolyte allows ions to move in and out of the polymer. And so when I switch it on, it's not only the field effect carriers, but it's all the other carriers that we've created, turned on and off in the polymer. And so you get huge currents. And here's another one where we can dope the semiconductor and the transistor in different ways. So let's mainly look at the electrochemical transistor. So first of all, how do you make a porous organic semiconductor? And this is the work of Ximin Zhuang. And so this has been in the literature for a long time, but nobody really thought of doing this. But as I make a solution of an organic polymer, and the organic solvent slowly evaporates, and if I do this under a very high humidity atmosphere, the water stays, and the water droplets organize, and when it's all finished, I have a material with holes in it. So it's a porous, and we can tell that it goes all the way down to the electrode here. And so this just shows you more, and it's not super regular, but what we're going to do with it, this is satisfactory. Here's the polymer, there's the void, and you can see that here. So what are we going to do with it? So, by the way, for the students, if you want to read a review on this topic, this is Yao Yao, current research professor in my group, really a brilliant scientist. So here's the organic electrochemical transistor, and it combines what people call iontronics. You notice now there are carriers not just on the surface of the semiconductor, but all the way through. We can tell that with a lot of different analytical techniques. Okay. It gives you very low operating voltage. It's biocompatible. Some of my colleagues said, yeah, but you got a liquid electrolyte, it's going to evaporate. That's silly. I said, well, suppose the electrolyte is blood or serum or a biofluid, which has salt in it, so it's a conductor, ion conductor. So we get all of these possibilities, and you can tailor it to make it biocompatible. And here's just things that are in the literature, or some things I'm going to show you. You can do all sorts of things with these transistors. We tend to express the current as the transconductance, because this is also a measure of its ability to be part of an amplifier. And so I'm going to show you some pretty wild stuff. So what kind of a polymer do we want? Well, this polymer has to have redox properties. I create holes in the polymer with the electrochemistry, and those are, of course, are electrons, and they conduct. But we're going to do more than that. As I create these positive charges or negative charges, counter anions have to flow in through the porosity. And so we put these ethylene glycol groups, polyethylene glycol. Those actually are known to facilitate cation mobility. And so this is just showing you some data. But for example, this is a honeycomb. We call it honeycomb H. So we learned how to do the breath patterning just the way. Let me just go back for just a second. Whoops, sorry. So we learned how to do this with those particular polymers that I showed you. And I'll show you some more data in a minute. But what's interesting is, so this is the current. The current of the honeycomb one is much higher. This is a log scale. And Liang Huang was one of the people who worked on this. But one other thing that is interesting is you begin to think about it, and we've done finite element analysis. This porous material, think of a Brillo pad. So if I have a steel wire and I stretch it, it'll break. But a Brillo pad is all these interlocked materials, and so you can you can get, and it turns out the structure actually releases a lot of the strain on the material, so you can stretch those. I'll show you in just a second. Yeah. So these are some that we've done, and it's on styrene electron. This is a flexible polymer. I don't know why it stops and starts, but so you can see the stretching here. And here's another example here. But you might say, oh, I bet when you stretch it, the mobility just drops to the floor. No, it doesn't, in fact, because, and part of it is, we go back first, no, it won't stop. Part of it is because we've stretched it, but the electrical connectivity has not been destroyed. So this is a machine we have to do the stretching and measure the mobility. And so you can see we can. But you can see here's the transconductance with strain of one of these materials, and it changes very, very little. And here's just showing, so you might say, yeah, well, it did it once and then it'll die. But no, here we have number of cycles up to thousands, and you can see very, very uniform mobility. So these have the mobility that you want with the transistor, and yet they can stretch. And again, this just reminds us of what the device looks like with a liquid electrolyte here. So liquid electrolytes have very high dielectric constants, and that's something you'd like to have in a transistor. So what can you do with these? This is one of the things we've done. We've made a device for measuring heart function. You'd like to have that and to be stretchable and flexible for the patient. And so this is just showing we can stretch it, say the patient is doing whatever he or she is doing, and the heartbeat signal as we stretch it this way, here's the source and drain, or the other way, it's very, very stable. And you can print these the way you could print, simple newspapers. So then along comes Wei Huang, who did something amazing, had an amazing idea. So this is the electrochemical transistor, and so the ions have to move from the source and drain. But he flipped it around. He said, well, what if I make it vertical? Okay, so now the source and drain are very close together. This is going to be like 70 nanometers, where this is microns. So we'll make something like this, vertical circuitry. And I'll show you some data in a minute. This came out in Nature early last year. And so this is the fabrication. I'll go through pretty fast, but it's very simple, in fact. So here's the semiconductor. You're basically doing that. And then we use silver chloride electrode. And so this is just the equation for the transconductance. And this, of course, is related to the dielectric constant. So here's the mobility. So I'm going to show you in a minute some huge transconductances as we go from here, the conventional organic electrochemical transistor, to the vertical one. And what's interesting, and I don't have all the answers, but when this distance gets to be 70 or 80 nanometers, the ions are moving in and out very, very fast. And why is that? And there are people who have shown in other work that when you confine certain polymers to small dimensions, their glass transition temperature changes from the bulk. And that probably is the best explanation. We've done a lot of experiments to show this is quite reproducible. So this is just sort of showing the fabrication process again, except now I'm showing you the polymers. So you notice they have these ethylene glycol, polyethylene glycol ones. And there's something else we invented, and I showed you once already where we photocross-linked a polymer with a cross-linkable blend, and you get phase separation. And this one is, it's actually a cellulose, so it's nature made. We photocross-link it. So this is the electron microscopy. So here's the semiconductor here, and then we're looking down at it. And these are some of the ingredients. And now let's look at some data. So these are p-type, and this is the vertical organic electrochemical transistor, and this is the C means conventional. So if you look at the transconductance, it's 150 here, and it's 12 here. That's p-type. The same with n-type. So here's the transconductance for the vertical device, and the transconductance is, let's see, where is it? It's over here, sorry. It's as high as more than 100. And for the conventional one, the transconductance is about 6. So it feeds back into what kind of an amplifier you could make. And this is just sort of where we stand compared to all of the literature. So these black ones are our data, and the red ones are the literature. Oh, sorry. Okay, the stars are our data, and red and black, and the other ones are literature data. So this we think opens up a whole new vista in terms of what you can do with transistors, soft matter transistors, stretchable. So the transconductance goes up a huge amount. And this is just, you may say, well, yeah, but what's the stability like? So this is just showing cycling a lot of times, and you can see very high stability. A little bit of deterioration. I can't tell you for sure whether it levels out, but very robust, very stable devices. 50,000 cycles, and at 1 millisecond transient times, and that beats any other electrochemical transistor. And so the other thing you can do, if I have p-type and n-type material, I can make a complementary circuit. And there are lots of reasons why you want to do that, but it has to do with the efficiency of how you use the electric current. So this is a complementary circuit. And this just shows you how you make it. And here we've made an inverter, and you can make thousands and thousands of them by this type of lithography. It's very simple to do. Very stable and very good performance. This is the Hui Wang again, his work. So now I want to switch gears. We've talked about organics, and maybe there's some inorganic people in the audience who say, oh, that's organic stuff. I can't tell one of these funky-looking polymers from another. They all look the same to me, and I can't figure out the names, where the names came from. So let's do something a little bit different. I'm going to use oxides to make transparent, flexible electronics. And this is just dreams that people have, but here's an example. Here's a heads up. Suppose for your car, on the windscreen, you would say here, you have a decal. As simple as that you stick on there. They would tell you the speed or whatever. You don't need any fancy display. This is from Samsung. And now let's talk about the oxides. Here's amorphous silicon. So in lots of the LCD displays like this iPhone here, not the OLED one, the pixel size is limited by the size of the backplane of this laptop. it's called the backplane, and that's a network of transistors that turn the pixels on or off. Well, if you have a material with higher mobility, you can make much smaller pixels, higher density. And this compound here is called indium gallium zinc oxide. How many people have heard of IGZO? Okay, 2 people. Okay, so at least the students are not saying, oh boy, the same old IGZO stuff. This was very, very important. Sharp developed it, and it's the reason that Foxconn bought Sharp. So let's say a little bit more about it. So everything we learned in elementary physics, for example, solid-state science, you want to have a really conducting material. You want to have a perfect crystal, right? Is that true? So suppose you could make the crystals, the material amorphous, by maybe growing the films at low temperature, other kinds of tricks. So by amorphous, I mean that it's not a random mixture of oxide and metal, but the organization at the length scale beyond the coordination sphere is random. And here's a material here. This is the electron diffraction. Here's the XRD. There's almost nothing. So where's the Bragg planes? So what is interesting about them is if you do it right, you can get very high carrier mobilities, comparable to a single crystal. There are no grain boundaries in an amorphous material. Low deposition and temperatures, you say, what's the big deal? I want to grow them on plastic. That's the big deal. So I want to go at low temperature. Very smooth, no grain boundaries, mechanically flexible, optically transparent, properties tunable between insulating, semiconducting, by doping. So we ask, we're always asking something that is tough. Are they compatible with organic materials? Could you grow these films from solution? So the original work was done by a man in the UK named Billingham. And people really didn't pay much attention to it. He said, oh, I grew the films at low temperature and I had very good mobility. And everybody just said, don't waste your time. But Hideo Hosono at Tokyo Tech said, wait a minute. That's something really interesting to try to figure out why that might be. And I think the best theoretician is Julia Medvedeva. And here's what's going on. And there are other good theorists as well. So for most of these materials, like, say, ITO, so these are late heavy metals. The valence band is mainly p orbitals. This is the energy. This is the density of states. The conduction band, say if I had indium oxide, is empty. But they're very spread out. They're very, very dispersed. And so if I dope it, say to make ITO, then I put carriers here. For a transistor, of course, we don't want to have carriers here. But we can ask, what are the limitations and implications of this picture? You see, if this is a big spread, it's optically transparent, right? If it's like more than 3 EVs, it's going to be really transparent. And if I have good mobility, I've got something really pretty interesting. And can we use these for electronics? So I'm going to give you sort of an abbreviated discussion of some of these points, but here's one of the first things we did. We grew, this is a transistor where ITO is the gate dielectric. There's glass here, or PET. This is a gate dielectric we've developed, self-assembled nanodielectric. And here's the amorphous oxide. This one is zinc indium tin oxide. And we're going to grow it by pulse laser deposition. So this is a matrix of 100 transistors. And remember we were talking about the amorphous silicon having a mobility of 0.5. This is 160. And if on silicon dioxide, it's about 20, but if on this special gate dielectric we've developed, it's 160. I first showed this at a conference, and Hosono jumped up and started pounding the table. He gets very, very emotional about these things. He didn't believe it, and we convinced him that it's real. And this is just showing some of the data, the transfer plot, and minimum hysteresis. So just a quick aside, we made a gate dielectric with, and actually this was an NLO material, Alex, but we said, let's try it as a gate dielectric, and it's phenomenal, and we could go into all sorts of reasons, but it's as good as Intel's hafnium dioxide. We get very high capacitances, and so that gives you very low operating voltages. The other thing is, so if you really want to do this, you don't want to have, so Samsung, in terms of the IGZO that they sputter, this is giant, million dollar sputtering machines. It takes 30 minutes, we think about 30 or 60 minutes to do a very simple IGZO layer. We developed it, and this is Myung-Gil Kim. The idea is, you may remember as a kid, the thermite reaction. How many people remember that thermite reaction? You mix aluminum and iron oxide and you warm it up and it gets really, really hot. Well, this is basically the idea here, to make the film that we're casting self-heating. So we don't need furnaces, we don't need all sorts of fancy stuff. We just spin coat it and warm it up a little bit, and it smokes a little bit, and we get very, very good transistors. Yes, you might say, yeah, but can you really scale that up? And so this is Professor Yu now, who did this. He looks younger there, a little bit younger. And the idea is to do the combustion synthesis, but do it as a spray. And so you can cover huge areas. And you say, well, how good is your IGZO? Our IGZO is just as good in defect density, mobility, and porosity as the magnetron sputtered IGZO that Samsung makes. And so here's a display. This is just one of Microsoft Surface one, but they use, so you make the transistors out of IGZO, and we can do it with a simple photo patterning. Well, Binghao Wang said, I got a better idea. I'm going to make fibers. I'm going to make IGZO fibers, oxide fibers, and this is his idea. And basically there's gas flowing here and the solution, and you get all of these beautiful fibers. And he calls it Fibertronics. And you can show that, again, because imagine the Brillo pad is the extreme, but you can stretch it a lot. You stretch basically the network of fibers, and you can show quite good mechanical properties, and you can make a strain sensor. And some of this work was done by people who do finite element analysis to try to model how the strain is dissipated. But Binghao said, oh, I'm going to make devices. So here's a strain sensor using and FN means fiber network. And here's a strain sensor. This is a photodetector. This is breath analysis after drinking beer. And we were just talking about alcohol on campus. I won't say where this experiment was done. But it works, so you get patterns. And this he pushed to an extreme, so you can make all sorts of fiber network, integrated electronics, very simple fabrication. And so in one patch, you can do all these different measurements. You can have ITO fibers, copper oxide fibers, IGZO fibers, and so we think this is really pretty neat. So the last topic, right on time. So I've talked about these wonderful organics that are stretchable, flexible. We've talked about the oxides, which have some flexibility if it's amorphous. What would happen if you basically, so lots of transparent conducting oxide science and technology is based on doping the oxide, so to fill that empty conduction band. And so we had the idea that let's do the combustion synthesis, but let's mix a polymer in. And this is PEI, which is very electron rich. So essentially it's going to dope the indium oxide. And just to sort of give you an idea, so as you add more and more of the polymer, to the indium oxide and do the combustion synthesis. So we use indium nitrate. So that's part of the combustion. It's a strong oxidizing agent. You can see that actually the mobility of the indium oxide, when we dope it with a little bit of PEI, really goes way up, and then it levels off and goes down. And you can basically model it. You sort of say, if I have indium oxide, this is its intrinsic properties. But as I begin to dope it now, it turns out that indium oxide has oxygen vacancies. If we fill those with this polymer, and we've done XPS, XFs, X-ray diffraction, everything you can imagine, you reach a point where we filled all the traps. This should be traps and not wraps. And it maximizes. And then as you add more and more polymer, ultimately it's filled the traps, but you begin to lose mobility because there's less and less indium oxide. So you might say, yeah, you got lucky. You tried one oxide and it worked. You tried one polymer and it worked. And so this is just showing you a whole group of polymers. We've made transistors of them. And basically, the mobility scales as the work function. So the more and more electron-rich the polymer is, the more and more it fills the traps, and you get, here's the nitrogen content and the mobility, and the work function and the mobility. So it's reasonably linear. So this is the work of Jiming Wang, and what he was looking at, this is a machine he made to actually measure the mobility as we flex. So this is basically indium oxide with just a 1% PEI, and we've made the indium oxide, and it's on a flexible plastic substrate. And here you can see it can flex back and forth, and the pale yellow color is the PEI in the polymer matrix. And this is just showing as we bend the device more and more. You retain most of the mobility until and we begin to finally lose it. So this is no PEI, and this is more and more and more. And you can see at this level, we've really kept a lot of the mobility. You can make PET polymer indium oxide TFTs that you can bend. And these are different organic dopants that we use. And it works very well. And let me just do one more thing and we'll finish. So this is what's called an electrolyte gated transistor, and we already showed those. But what we're doing now is, and I'll show you, this is called an electric double layer transistor because you have both holes and electrons at the two interfaces to the electrodes moving, and you get quite respectable transconductance. But I want to take this one step further. So IGZO is a great N-type conductor. Most of these polymers are P-type. There are a few that are N-type. So here's a device that's a complementary circuit. So here's the IGZO, the N-type inorganic, and here's the P-type, which is the electrochemical transistor. And we've made it porous, so it's flexible, it's stretchable. We make inverters, all of these things you'd really want to do. And if you could do that, this is an example that Yao Yao did. And with Antonio, and what we're looking at, and at first you might think, oh, this is kind of silly, but what we're doing is looking at eye motion. So people with sleep disorders, you want to see their eye motion, and you can immediately identify if they have some kind of sleep disorder, and other kinds of eye things. And when we make this little amplifier, which I just showed you, this little inverter amplifier, just this little patch, and you put it around your eyes, and it picks up the electrical signals. with a control, it's very the signal's very weak. With that little amplifier that I've just shown you here, it's really quite strong. So ultra low voltage amplification possible. Okay, some conclusions. We've sort of had a journey here. We've done some soft materials. We've done some hard materials. We've blended them together. And so we started this journey trying to figure out rational, ways to print ductile, optically tailored materials for unconventional electronics and solar cells, which I haven't talked about. And so we know a lot more in the last couple years about how to make ductile organic semiconductors. We've learned a lot about how to hybridize the organic and the inorganics. And this includes, of course, the electrochemical transistors. I haven't talked about polymer solar cells at all, and I know this is one of Alex's. There just isn't time. But a lot of the things what I talked about, tuning the band gap, tuning the organization, are applicable to solar cells. And the last thing, which maybe I should have made more of the lecture on, is the very importance of theory, modern theory, to say, gee, I'm thinking of making this polymer. What's the band gap? The day is here when you could calculate that, where you could say, oh, this is a waste of time. Don't put another group here and there. And we're going to see more and more of that. And it's, I think, really, really fascinating. So theory and modeling are essential as we go forward to optimize materials. So let me give some acknowledgments. Some of the people probably are in this audience. This is our campus. It's on Lake Michigan. Here's the city of Chicago. There's a beach here, and there's bicycle paths here. And this is the student center here. And lots of collaborators from all over Asia and Europe. And I'm going to show you a picture taken on the Lakeville. This is our summer picnic. And I don't know what that means. Oh, so this is people from all over the world there, and we don't have any age restrictions. So we don't say, well, you're too young to be a chemist. So with that, but keep out of the lab. With that, let me conclude. Thanking everybody for the hospitality, and I hope in the next couple days I get to meet more people. And so thank you very much.
So thanks, Professor Tobin Marks, for the spectacular talk. So now the talk is open for questions. We would like to invite the question from the students or postdocs. Okay.
We tried an experiment at Northwestern. The department chair says, I'll give $5 to each student who asks a question.
So I just checked with IAS, right? So anybody, okay, asks a question, you will have $50 of Hong Kong dollar. Okay.
It has to be a scientific question.
Scientific question.
Instead of the money, you are invited to the tea party tomorrow. Yeah. So coming to have opportunity with Professor Marks free tomorrow. That is your ticket.
Okay. $50 equivalent ticket. Okay.
So save your questions for tomorrow then.
Okay, Shinger. Okay, maybe you.
But he doesn't get 50 Hong Kong dollars.
Yeah, but I think so. It's need to warm up, so then the students can follow up with the question. Yeah, thank you, Tobin, so for the very wonderful talk. And so I feel so it's your group really did a very excellent work. So especially after I left the group.
They said, boy, I'm glad that guy's gone. Now we can.
Yeah.
No, people remember you. Believe me.
Yeah, thank you. So my question is, you did quite a lot of work on the oxide, and the oxide, the mobility is typically higher than organic. Well, if we want to make the electronics into the complementary circuits, so we need to both P-type and N-type. So probably P-type materials is better to choose organic rather than oxide.
That's right. That people have tried for years to make P-type. There were different reports in the literature, different copper oxides, different sputtering techniques, and not really, maybe they'll get a mobility of 1. And it's not even really understood what's going on there.
Yeah.
And if I take other types of inorganics, which are P-type, they're not transparent.
I see. Well, if we use all the organic materials for the circuits, so the N-type materials may also suffer from the stability. So
it's getting better. It's getting a lot better.
I see. I see.
That N2200 is really quite air stable.
Okay. Okay. Thank you. Thank you for the comment. Okay.
Yeah, Angus?
Maybe I just speak louder.
Yeah, I can.
So,
of course, I'm right. I'm very close.
so you're working on amorphous metal oxide material together with the polymer substrate, so they have a different mechanical properties. Actually, we work a lot in solar cell, right? We have metal oxide together with the polymer. So I'm wondering if we talk about stretchable, is it compatible? For stretchable, right?
I think you need to play around a lot with the material. We've made some stretchable, but the other thing is maybe you can do better than ITO, but so there are people who use nanowires, but everything like that reduces the optical transparency. So I guess the answer is, to date, people have made bendable solar cells and some stretching, and we're working on that, but it's not as dramatic as the transistors there. But the good news is that if you get the match with the inorganic, you're not going to have to worry about the organic not being stretchable enough, which was a problem, say, 10 years ago.
Maybe I have a follow-up.
Sure.
You have shown a very wonderful mobility of your metal oxide on your sand dielectric.
Right.
But you also have a silicon dioxide layer as a protective layer between them. So is there any reason, right, you have a higher mobility on top of the
that
sand?
particular experiment, we were using PLD, pulse laser deposition, and it turns out that very thin layer of silicon dioxide protects the sand from the laser damage. But when we do it the other ways, we don't need that layer.
I think so. You actually grow the same on the silicon oxide, right?
Right.
Because
right.
you need to, that same really is a silane type of
Heavily cross-linked.
same, right? Okay, so that need to develop, grow on the silicon oxide. Just like,
You also have a protective layer on top.
Right, because on top of what Alex mentioned, we then grow indium oxide by pulse laser deposition. So that you can do at low temperatures, but it turns out you get some damage from the laser.
I'm just wondering whether there will be morphology crystallinity difference if you grow it on top of the sand or the silicon dioxide.
Oh, well, of course, it's an amorphous material, so it may be harder to tell. I think we've done XFs, and we don't see any dramatic differences, but that's, it's funny about amorphous material, because the first thing, an oxide guy would do is say, let's do the XRD, and of course, you don't see anything.
yes, Xiaochen.
Thank you. I was really fascinated by this porous semiconductor you mentioned. Are there any study to give you a general trend between the mobility versus porosity? Any trend, like, are they correlated tightly, or any study?
Yeah, I mean, because if you sort of, let's see, maybe I can draw on here. I don't want to draw on a blackboard that you're not supposed to draw on. But let me just go back. Let me just go back to the picture of the oxide of the. If I keep turning it off. Well, I could do even something like this. So you can see, obviously, you've got much less semiconductor here, and they have to obviously go around these pathways. So the mobility does go down some. But on the other hand, when it's an electrochemical transistor, I mean, you get these enormous transconductances. I think we're okay now. So it's a trade-off. But because these are mostly amorphous, it's not as if you're interfering with the packing. Sorry, just a second, let me go back. I mean, you can see here there's lots of semiconductor missing. But the other thing is the electrochemistry we do to dope the electrochemical transistor, the flip side is that you can make very high densities of carriers.
Yes, Damian.
Thank you. Hi, Professor Marcus. So this is Dayuan. So a very nice talk. So a question is related to the previous one. So you use some chemistry method to produce such porous semiconducting polymer films, but this is naturally a bottom-up method, right? So you control the.
And you can do it on a huge scale, of course.
Yeah. So my question is that can we also apply some top-down method? So for example, you produce a self-assembled polystyrene microspheres layer, and then you do your spin coating of polymers, right?
So the block copolymer technique that
Okay.
Tom Russell and others have done, Frachet. Intel looked a lot at that for making patterning at a very small length scale, and I don't know whether it's been commercialized or not.
Okay.
But no, that would be the other way to do it.
Yeah, because it's easy to control the density of pores, right? Medicines you can control.
We can do it to a certain extent by manipulating the solvents and the time of the evaporation. We really haven't sort of pushed it too far. We were more interested in just seeing if we could make it porous. What the motivation was. People say, well, why did you make it porous? And so there's an answer. Yeah. But we can certainly do more.
Yep, Jinlei. Yeah, maybe wait there for microphone.
Your microphone is on the way.
Yeah, there's one work on blow spinning with fibers. From your results, we can see that it has very good durability. I would like to know what is the mechanism for endowing such durability. Fibers are fused together, or fibers can slip relative to each other. I think normally fibers can move relative to each other.
You mean it relieves some of the stress when you stretch them, but because they can move, you mean that's what you're asking?
Yeah, that can improve the stretchability. However, how to ensure the durability, the strength?
You mean like multiple stretches, or you mean air durability, or?
Yeah, repeatability is one thing. Yeah, very very important. Once they can sleep, when you stretch, they are going to really fall apart.
Let me see. I don't know. I don't remember whether we have any that data here. Let me just go back.
I saw you. It's a blow spinning fibers. Also, your student called that fibertronics.
Binghao Wang, yeah. So I guess what this is a theorist, Professor Yu, who moved from University of Houston to Penn State. I forget, I can't pronounce he's a really good guy, how to say it's, does anybody know him? Okay. Yeah, okay, thank you. So he worked out a lot of that, and I think so. What his idea was that you have these fibers going in every direction, and so stretching them relieves moving them that way. They begin to align with the strain field, but you're not doing that. So I don't know whether that's So you can see here, you can get this far where it recovers, and then beyond that, they begin to break.
Yeah, I think here is the strain. This is sort of a piezoresistive. Piezoresistive. When you put some strain and its resistance will change. So that's very sensitive. That's very good. But yeah, how can this material be repeatable? Because
I guess,
fibers
yeah, most of the
normally,
bending
they are
he's done
relatively
is more like this than that. Take a look at this Nature Com paper, and if you really have other questions, I'll put you in touch with Bing Hao.
So I suggest that tomorrow morning you will have a breakfast with Professor Marks, right?
10 o'clock.
10 o'clock. Okay, so
That's a late breakfast.
late breakfast?
Is that tea or breakfast?
Yeah.
I have no awareness of.
So then you maybe I suggest that then you can discuss more details.
Yeah,
Okay.
okay.
During your encounters there. Okay.
Thank you.
Any other questions? 徐珍姐，有没有 question? No? How about 运气? No? Okay. Oh, yeah.
Many thanks for your presentation. So I just want to know the selection rule of the materials, because you talk about many of the microstructures of the material. So we just want to know the selection rule of the materials.
I guess it depends on the function you're looking for. I mean, do you want strength? Do you want optical transparency? That would be what is the cost? If you're going to make huge amounts, maybe indium oxide is too expensive. So there's a whole bunch of parameters.
Yeah, I think Xiaochuan have another question, right? So.
Oh, I was wondering, you showed this vertical electronics and published in Nature this year. So other than dimension, what make vertical much better than horizontal?
Oh, because you can get the source and drain very close.
Okay, that's the dimensional.
Right.
Just that one factor.
Right. Yeah,
Make
it turns out, so we have 2 manuscripts under embargo with Nature journals, and there'll be more coming out, but I'm not supposed to talk about it.
Any other questions? So
You
I
didn't
have
get
one
a
question.
chance to spend the 50 Hong Kong dollars.
Okay, because Su Han said she will not give that, but I only give that as a ticket, right? Okay. Okay, so my question is a philosophical question, right? You have a colleague just across the hallway, John Rogers, right? Okay. But then you work a lot on the either organic or the transparent oxide, and also for this transistor application or biomedical
So
application.
why don't
right?
we collaborate, you mean?
No. I mean, but
No,
most of his application is all based on the silicon, right? Okay.
That's probably why we're not collaborating.
Yeah.
But I
know that.
I
That's the
respect
difference
his
between.
work very much.
But then, my question is, right? If you give people some perspective, right, for pros and cons, okay, right? Involved in silicon. Both of you are very successful scientists, right? But then you are working on a very exciting fields in that. But then one is based on the traditional semiconductors, like a silicon, okay. But then another one is based on this innovative semiconductor, either based on organic material or transparent oxides, right?
Or some
So-
hybrid.
or hybrid system in that. So if you would like to give some people some direction or the perspective, okay. So what's the pro and cons, okay, in this area?
I think, of course, the silicon fabrication, a lot of it is, job shop type things. You can get it made. Whereas if you're making new kinds of polymers, you have a lot more to learn. I think probably the winner will be some combination of both.
Okay.
Yeah, I've talked to Rogers people a lot, and it's sort of like, where do we start if we want to collaborate? And we haven't sort of found one thing that where John says, oh boy, if we could only do that, bring your materials. So, but he's well aware of what we're doing and vice versa. And he's not across the hall. He's probably, what would you say, Shinga? 100 meters away, 50 meters away.
100 meters away. Okay. So if no further question, please join me to thank the Professor Tobin Mark.